Hey, how are you? Good evening. Or should I say good morning? My name is Mark Soltys. I am the Orbital Mechanics Engineer here at Earthrise Space Incorporated. I am the newest intern, and I am excited to be a part of Team Omega Envoy. We are competing in the Google Lunar X Prize. My job here at Earthrise is fairly simple. I am here to optimize the trajectory that our lunar lander takes from the Earth to the Moon. All of that is done through simulation in a program called SDK. SDK stands for Satellite Toolkit. In a nutshell, SDK is a physics-based software that allows engineers to create various scenarios. Each one can either model different parts of the mission or different situations that may arise. For example, our orbiter gets stuck in a circular orbit around the Moon and we have to figure out our way to get down. Maybe we lose power on our translunar injection towards the Moon. What can we do from here? How do we communicate with various satellites around the sky? And any other situation, honestly, that could happen. It's a very powerful program, and I'm excited to be learning the program and working with this team. They're very motivated, and it's really neat to be able to take what I've learned in class, expand upon it, and apply it, and see it used in real life situations. What I'm going to do today is to take you through a very generic overview of one of my jobs. What I will do is teach you how to go from the Earth to the Moon. To do so, I will do that in 3 phases. The first is the launch phase, which we will cover a couple different ways to launch using different approaches. Then we will go into the injection phase, where we will move from the Earth to the proximity of the Moon, and the last phase, which would be the approach and landing on the Moon. I will break those down in simplest form as possible, not apply any numbers or anything, that way neither yourself or I get confused. Should be a fun journey, and let's get started. Okay, the first phase in getting from the Earth to the Moon is the launch phase. In the launch phase, there's 2 methods that are preferred. The first is the direct descent method, and the second is the launch coast burn method. Both methods leave from this big guy called the Earth. Say we launch here from Kennedy Space Center using the direct descent method. We're going to launch off the surface of the Earth, and we're going to go ahead and begin our trajectory towards the Moon. The second method, the launch coast burn method, follows the same path to begin with. We're going to launch, and then we're going to enter a parking orbit around the Earth. Hopefully a little more symmetrical than mine. What this does, this allows us the freedom to launch and go to the Moon on essentially any day of the month. Our launch time will control the right ascension of the ascending node, denoted as RAAN. And what this does is allows us to adjust the orbit plane to contain the Moon. And then our coast time, which is the time that we spend orbiting the Earth here, will adjust the apogee of the transfer orbit to include the Moon. And essentially both methods now have us into our next phase, which means we are off the Earth, and now we are ready to start our trajectory towards the Moon. Right, in the next phase of our lunar mission, we will begin our transfer to the Moon. Most transfers to the Moon are a ballistic transfer. For example, we can get a better image if we draw an ellipse, like so, if you can see that. Here we go. And we'll center that here on the Earth. And of course over here we're going to have our perigee, And on the other side, we're going to place the moon over here at the apogee. Neglect the effects of gravity of the moon, and it makes this a little bit more simple. Essentially, we are looking at an average launch time from the Earth over here to the moon of about 5 days. To shorten that time, you're looking at doing an accelerated burn through your translunar injection, also denoted TLI, and in which case you will undercut the moon and you will have to do what is called a lunar orbit insertion to capture the moon, which is denoted as LOI. To give you a better picture of that, we will draw the Earth and the moon on the same axes, oriented with one another, like so. And what this is going to do is put the moon over here and the Earth down here. So if we launch on a normal 5-day trajectory, launching over here from the Space Coast, we will come around the Earth and we'll capture the moon. To shorten this, we will launch, same method, and we will accelerate that trajectory. And for a better example here, so we're looking at about 5 days, maybe 4 to 3 days here, about a 2-day trajectory here. You can see as we come around the Earth here, and you're looking at our trans-lunar injection phase here, and our lunar orbit insertion here, putting us around the moon. The last method here, not necessarily a method, but a technique to expand your available launch days is called phasing orbits. To give you a better picture of that, we will again draw the Earth over here, and we'll just put the moon per se over here. You can see that on the other side of the board. What you're going to do in a phasing orbit is essentially launch off the Earth. Say you have nice weather, everything's good to go, just go ahead and launch, and you will enter what are called phasing orbits. Right? And you're essentially just going to keep orbiting the Earth, putting the Earth over here at perigee, and a second orbit, third orbit, and let's say now your calculations come together, your planes have lined up, and now you're ready to go to the moon. So you will come back around one more time, and you'll begin your trip to the moon. Phasing orbits, again, like I said, are just great to optimize your launch window, give you more opportunities. Adverse weather, especially say here in Florida, again, that's another advantage that people have used multiple times, utilizing these phase loops. And that's essentially it here for the transfer station to Alright, once we have completed our transfer to the moon, we are going to now begin our approach to the moon. Once again, 2 methods utilized here. The most abrupt will be the direct landing. You essentially have your transfer trajectory, and you're going to target down to a landing site. Essentially what you see here is a direct method. You have targeted your site, disregard all of this, you're going to come to the moon, target your site, perform a retrograde burn, and you're on the surface. The other approach is to skip this step here and enter a lunar parking orbit. The lunar parking orbit method is more complex, but the benefits outweigh the troubles that you have to do to get there. We'll go ahead and cover that now. So we've left the Earth, and we're coming to this guy, the moon. And so we will come into the moon on our translunar injection, coming from all the way over here, and we'll go ahead and perform our lunar orbit insertion, which is essentially a retrograde burn, which means we're firing against the direction that we're going. And that is going to slow us down into this parking orbit going around the moon. Once we're in this parking orbit, we've essentially caught the gravity of the moon. We're orbiting the moon just like we were orbiting around Earth just days prior. This is not a very long phase. We're essentially here for maybe 1 or 2 days. we will perform what we call a descent orbit insertion, which is going to take us out of here, down into a lower orbit, and then we're going to come down to the surface of the moon. Our next phase, we're going to cover a few targeting methods, but essentially here we are, orbiting the moon. We're ready to start going down to the lunar surface. Alright, the next phase, one of our final phase, is targeting our landing site. For the direct method, this is very simple. You've essentially targeted your landing site, adjusted your launch time, your trajectory from that landing site, so you're going to perform a retrograde burn, come down to the surface. For the lunar parking orbit method, however, this is a little bit more involved. In the parking orbit method, you have a right ascension of the setting node, as you remember from earlier. And again, this is based on, or like relative to the Earth-Moon line. And it is going to be based on your time of flight. I can, for a better visual here, I will show you how time of flight affects your right ascension. And so, as your time of flight is lowered, you're essentially going to move your trajectory closer to the Earth-Moon line. If you remember the drawing from earlier, where we showed the 5-day, the 4-day, the 3-day trajectories, you can see how they start to get more linear the lower number of days it takes you to transfer. And so now when we're looking at the moon and these particular transfers, we can see that here, running right down the center, is our email. This is our Earth-Moon line. And right in about 3 days, we're looking at an orbit coming somewhere around here. So this is about 3 days, right? And right across here, you're looking almost completely perpendicular to the Earth-Moon line. It's about a 5-day trajectory. And somewhere right there in the middle, you're looking at a 4-day trajectory. So what you're looking at here is the longer it's taking me to get to the moon, you can see me start skewing off this Earth-Moon line and phasing up here, almost here to our 5-day trajectory. And so how can you fix this? How can we adjust our plane here to land on our specific targeting site? There's a handful of ways to do it. The first one, you can adjust your time of flight. So say you're on a 5-day trajectory, well maybe that's going to skew you way off the Earth-Moon line, so go ahead and speed yourself up. And lower that trajectory, get yourself into a 3-day, maybe a 4-day, and put you over close to your landing site. The other one, you can just stay in orbit longer. So if we're orbiting out here, we can just let the moon rotate underneath us until we line up with our landing site, and we can go ahead and retrograde burn down to the surface from there. And the last method is, like we talked about earlier, phasing orbits. So instead of maybe coming out to the moon, and where the risk is a little bit higher, and you're further away from home here, you can go ahead and do phasing orbits around the Earth, and go ahead and buy yourself some time, and maybe you can essentially plot your trajectory straight on this Earth-Moon line. The final thing we're going to talk about here is the ascension down to the moon's surface. Alright, the last phase, which is the most exciting, are our powered descent trajectories. Again, the method that we always put on first is our direct method. This is essentially just going to perform a stage braking maneuver. You're going to slow your craft down to about 500 feet per second at an inclination of about 7,000 feet above the lunar surface. And you're going to brake yourself down from there using various descent methods, and this is where the two cross over and run about the same methods. From the parking orbit method, however, we're starting from a much different altitude. To give you a better picture of that now, go ahead and start with our moon. And here we are in our parking orbit. And as I said earlier, we're going to perform what is called a descent orbit insertion. This is going to bring us down to about 50,000 feet. So we will start to come out of our orbit, and we'll begin descending down to the moon here. Where we're standing right now is about 50,000 feet. Once we reach this periapsis of the moon, we'll begin a retrograde burn, essentially at about 10% throttle. See, there's a better way probably to show this to you. Here we are leaving our parking orbit, and here at about 50,000 feet. We can go ahead and look at the moon as a surface at this point. And so we're here currently at about 50,000 feet. Here's our little satellite, looks like a bow tie. And now we will go ahead and begin our braking. So once we are throttled up to about 10%, we'll allow our gimbal to align with the center of mass of our satellite. Once that is aligned, we'll go ahead and throttle our engine up all the way to 100%, and we're looking at about a 5-minute burn, which is going to take us from 50,000 feet all the way down to about 7,000 feet. 7,000 feet is called the high gate. High gate is an aviation term. This was used by pilots when they were essentially beginning their approach down to the airport. And from the high gate, we begin our approach phase down to the lunar surface. There's many methods out there for approach phases. The one that we will be covering is called the kinetic controller approach phase. And so I'll go ahead and blow this picture up and show you our approach phase. So here we sit currently at 7,000 feet, and right above the lunar surface, which is essentially flat now. And what we're going to do is begin to throttle our engine down to moving about 5 feet per second. What this is going to do is bring us down from 7,000 feet all the way down here, and here we're sitting at about 500 feet. And once we reach 500 feet, anywhere between 500 and 200 feet, there's going to be an algorithm that we utilize to control our ascension rate down to the surface using throttling control. So how that works, we're going to begin to maintain this ascent, and here we're looking for about 3 foot per second. This is controllable enough for landing gear, people inside, etc. Even if it's just equipment. 3 feet per second is a pretty common ascension rate down to the surface. What the algorithm does is it utilizes your mass, your velocity, and your altitude, and they're constantly updated inside this algorithm to make sure that you maintain this rate as you descend to the Earth or to the lunar surface. Your mass is constantly updated based on the fuel usage that you're using, and your engine will use the appropriate thrust to maintain this. And here you are, you land with your little lander on the moon. We get out, we put our little flag in the ground, and we make history. Essentially, this is our ultimate goal. Obviously, we're not allowed to, but I think any one of us would rather be this guy on the probe ourselves. Alright, and that essentially sums up our run-through of various simple back-of-the-envelope descriptions of how to get from the Earth to the Moon. We covered everything from launch to Earth orbit, direct ascension methods, translunar injections, direct orbit insertions, lunar orbit insertions, and various landing methods to get down to the surface of the Moon. Like I stated earlier, this is our ultimate goal, and this is where we'd like to be here in the very near future. Sadly, it's just going to be the lander, no human being. Not yet, at least. For more information in regards to our project and our team, feel free to visit us at megaenvoy.org. And there you can find team bios, Twitter updates, and pretty much everything pertinent to the project. Thank you guys for your time. I hope it was somewhat insightful. I'm very excited to be a part of this team, and I hope that you enjoyed your time here and maybe learned a thing or two today. Thanks again.